Okay, imagine this. You're standing by the road, maybe waiting for a taxi, and you hear an ambulance siren way off. It's coming closer, and the sound gets higher, right? That really piercing whine.
Yeah, you know that sound.
And then whoosh, it passes you, and suddenly the pitch drops. It sounds much lower as it speeds away.
Mm-hmm.
We've all heard that. I mean, it's a super common experience. But that shift, that change in sound, that's actually physics in action. It's called the Doppler effect.
Exactly. And today we want to give you a simple science summary of it.
Something really focused on what you need for your grade 12 physical sciences here in South Africa.
Precisely. Our goal is to unpack the Doppler effect, making sure it clicks with what's in your CTAP-yes document and what you'll need for the NSC examination.
So we'll figure out why that siren changes pitch.
Yeah, and also look at how doctors use similar ideas, like with medical tech, and even how it helps us understand the whole universe.
Wow, okay.
We'll break down the main ideas, show how they connect, and, why it's actually pretty useful stuff to understand.
Right. So let's start at the beginning then. Before we get right into the Doppler effect itself, maybe we should quickly touch on waves again. Because it's all about waves, isn't it?
Good idea.
Yeah.
Absolutely fundamental. I mean, the Doppler effect is a wave phenomenon.
So waves are basically disturbances caused by vibrations, moving energy around. But what bits about waves are super important for understanding Doppler?
Okay, well, the two big ones we really need to nail down are wavelength and frequency.
Okay.
Remember, wavelength is just the distance between, say, one wave crest and the next one, like peaks on a water wave.
Got it.
And frequency, that's how many of those complete waves pass by a certain point every second. We measure it in hertz.
And frequency is what gives sound its pitch. High frequency, high pitch.
Exactly. And for light, frequency relates to color. Now, the key thing is how they relate. Wavelength and frequency are inversely proportional, assuming the wave speed stays the same.
Meaning if one goes up, the other goes down.
Pretty much, yeah. If the speed's constant, like the speed of sound in air or light in a vacuum, understanding this relationship is crucial because the Doppler effect is all about changes in these properties.
So if the wave speed is constant and frequency and wavelengths are linked like that, what's actually, changing with the Doppler effect? Is the ambulance siren itself changing?
Ah, that's the really interesting part. No, the source itself, like the siren, isn't changing the sound it's making. The Doppler effect describes the change in frequency or wavelength that you, the observer, perceive.
Oh, I see.
It happens because there's relative motion. Either the source is moving towards or away from you, or you're moving towards or away from the source. It's about how the waves arrive at your ears or your eyes for light.
Okay, back to the ambulance then. So it's not actually getting higher pitch, but we hear it that way.
Yeah.
How does the movement cause that perception shift with sound waves?
Right. So picture the ambulance sending out sound waves, like ripples in a pond, but in all directions. As it moves towards you, it's kind of catching up to the waves it just sent out in your direction.
Okay.
This squashes the waves together in front of it. The crests get closer.
So shorter wavelength.
Exactly.
Okay.
Shorter observed wavelength. And because wavelength and frequency are linked, that means a higher observed frequency. And that's the higher pitch you hear.
Makes sense. And when it moves away?
Then the opposite happens. It's moving away from the waves it sent out towards you, so those waves get stretched out behind it.
Longer wavelength.
Longer observed wavelength, yeah. Which means a lower observed frequency, and you hear that lower pitch.
And this works if I run towards a stationary bell too. I'd hear a higher pitch.
Yes, the principle is the same. It's the relative motion that counts. If you move towards the source, you encounter the wave crests more frequently. If you move away, less frequently.
Okay, this is clicking. So for someone getting ready for their NSC exam, what's the absolute must-know part here? Especially with the math side.
Good question. For the NSC, you definitely need to explain the phenomenon clearly, like we've just discussed. And importantly, you need to be able to use the Doppler effect equation for sound.
Ah, the formula.
Yeah. Now, you don't need to memorize it off by heart, usually it's provided, but you must know how to use it. It connects the observed frequency to the source frequency, the speed of sound, the listener's speed, and the source's speed.
And getting the plus and minus signs right is key. I remember that being tricky.
Absolutely critical. Generally, think of it this way. If the listener and source are moving towards each other, the observed frequency should be higher. So you'll typically use a plus in the top part, the numerator, for the listener's speed, and a minus in the bottom part, the denominator, for the source's speed.
Towards means higher frequency.
Okay. And if they're moving away from each other, the observed frequency should be lower. So usually a minus for the listener upstairs and a plus for the source downstairs. You'll apply this to problems involving, ambulances, police cars, trains, typical scenarios.
Right. It's amazing how precise physics can be about something we just hear every day. But it's not just sirens and trains, is it? Where else did this effect pop up in a really useful way?
Oh, definitely. One of the most significant applications is actually in medicine, specifically with Doppler ultrasound.
Ultrasound, like for seeing babies?
Well, yes, that's one use, but Doppler ultrasound adds another layer. Doctors use devices that send high-frequency sound waves way above what we can hear into the body.
Okay.
Now, when these waves hit moving things, like red blood cells flowing through your arteries or veins, the waves bounce back. But because the blood cells are moving, the frequency of the reflected waves changes. That's the Doppler effect again.
So the machine listens for that frequency shift.
Exactly. If the blood is flowing towards the ultrasound probe, the reflected frequency is higher. If it's flowing away, the frequency is lower.
Wow. So they can actually measure blood flow without cutting you open.
Precisely. It lets them measure the speed and direction of blood flow. It's incredibly valuable for diagnosing things like narrowed arteries or finding blood clots, checking if heart valves are working properly, and yes, checking the blood flow in the umbilical cord for a fetus during pregnancy checks. It's non-invasive and gives vital information.
That is genuinely amazing, using sound shifts to see inside the body like that. Okay, so we've done sound, we've done medical tech.
Yeah.
What about light? You mentioned the universe earlier. This must be where light comes in.
Absolutely. This is where the Doppler effect goes cosmic, you could say. Just like sound waves, light waves, which are a type of electromagnetic wave, also show the Doppler effect.
So light from a moving star would change somehow.
Yes. If a light source, like a star or even a whole galaxy, is moving away from us, the light waves it emits get stretched out as they travel towards us.
Stretch, so longer wavelength.
Longer wavelength, correct. Now, think about the colors of visible light, the spectrum. Red light has the longest wavelength.
Okay. Red is long wavelength.
So when light from a distant object is stretched because it's moving away, its wavelengths shift towards the red end of the spectrum. We call this redshift.
Redshift. Moving away. Got it. And if it was moving towards us?
Then the light waves would be compressed, squashed together, shorter wavelengths, and the shorter wavelengths are at the blue end of the spectrum, so we'd call that blue shift.
Blue shift, moving towards... Okay, so what are astronomers actually seeing when they look out there? Red shift or blue shift?
Well, they see both for different objects. Some nearby stars show blue shift, meaning they're moving towards us. But the truly mind-blowing discovery, made largely by Edwin Hubble back in the 1920s, was that almost all distant galaxies show a red shift.
All of them, or nearly all.
Pretty much all the distant ones, yeah. And not just that, but the further away a galaxy is, the greater its redshift appears to be.
More distant means more redshift. Which means?
It means it's moving away from us faster. The further out you look, the faster the galaxies seem to be receding.
Whoa. So if everything far away is moving away from us, and faster the further it is, what does that imply about the universe itself?
It implies the universe is expanding.
Expanding? How?
Yeah.
Like, are the galaxies just flying outwards into empty space?
That's the common misconception. It's more like, think of baking raisin bread.
Okay.
Imagine raisins scattered in the dough. As the bread bakes and the dough expands, all the raisins move further apart from each other, right? But the raisins aren't like swimming through the dough. The dough itself, the space between them is expanding, carrying the raisins along.
Ah, so space itself is stretching.
That's the picture. The galaxies are like the raisins, being carried apart as the fabric of space expands. This widespread redshift is the primary evidence we have for this expansion.
That's a huge idea.
It is. And for your NSC, you need to understand this connection. Redshift observed in light from distant galaxies means they are moving away, and this is the key evidence supporting the theory of an expanding universe. You won't need to do calculations with light shifts, thankfully, but understanding the concept, redshift equals moving away equals expanding universe, is crucial.
Okay, wow. So we've gone from a passing ambulance siren to checking blood flow with ultrasound all the way out to seeing the universe expand. That's quite a journey for one effect.
It really is.
So bringing it back home for a grade 12 student listening, why is getting your head around the Doppler effect so important beyond just passing the exam?
Well, passing the exam is important, let's be clear, and this is a core concept in your SAP-PS curriculum. You need to define it, explain it for sound using examples, use that equation correctly, and definitely explain the significance of redshift for the expanding universe.
Right. ticking the boxes.
Yeah, but it's more than that. Understanding the Doppler effect helps you see how fundamental physics principles connect things. They explain everyday stuff, like the siren, but also these huge cosmic discoveries. It shows how science works, linking observations to theories.
And connects different fields like
Mhm.
medicine and astronomy.
Exactly. It builds your scientific literacy. You start to see the underlying rules that govern everything from sound waves traveling through air to light waves traveling across billions of light years. It's pretty powerful knowledge, really, and maybe something to think about after this. Given that redshift tells us the universe is expanding now, what kind of observations or maybe new technologies could help scientists figure out what happens next? Will it expand forever? Will it slow down? Or maybe even one day start contracting again?
Ooh, that's a big question to ponder. A great thought to leave us with. We really hope this simple science summary has made the Doppler effect clearer and maybe even a bit more fascinating for you. Keep asking questions, keep exploring. That's what science is all about.